All right, we are recording. Let's go from current slide. And yuck, I just remember. No, I think I said it. No, I forgot. Still have Monday. Okay. I want to go through with everybody all the end of the term type stuff. But with only one person here, let's just wait until more people get here. Right. And then before the first person needs to leave, then I'll go through everything. Okay. So let's go from here. Any questions on anything we've done so far? All right. So here's some of the properties of vector operations. Hopefully these make sense to you. We've talked about several of them before. Okay. If U, V, and W are vectors in the plane, we're dealing with only in the plane now, and C and D are scalars, any number, real number, okay, we're not going to deal with complex at this point. Real number, C, fraction, decimal, positive, negative, rational, irrational, it doesn't matter, just keep them real. Then, if you add vector U to vector V, it's the same as adding vector V to vector U. In other words, U plus V is equal to V plus U. Remember when we did our parallelogram method, showed that it didn't matter which order you did it, came up with the same result. It's the commutative property of vector addition. Now, I'm teaching linear algebra right now, and we're doing vectors too. And when I was teaching them yesterday, I couldn't remember. I said, we just did this. No, that was this class. So, and now we've gone further in their class, and I'm saying, haven't we already done this? I said, no, that was yesterday. So if I say, haven't we done this before? That's because we did it yesterday, but that was a different class. Here's the second. If you add vectors U and V, that gives you a vector. And once you have that vector, add W to it, that gives you another vector. So that last vector is the same as if you added V and W together, and then that gives you a vector. Add U to that, those will be the same vectors at the end. So this says that the vector addition is associative. Doesn't matter what arrangement you make of adding, as long as you're adding them all together. The third one, if you add U to the zero vector, remember zero can be a vector, and we're in the plane now, so that would be a two-dimensional vector, 0, 0, okay? Add U to that, and you still get U. That's the additive identity property of the zero vector. In fact, that's probably one of the few reasons we even have a zero vector, so we'll have that property. But also, if you add a vector to the opposite of that vector, you're going to get the zero vector. Now, normally, you might say, well, why can't you just say you're going to get zero? Nothing. Nada. Well, you can't really say that because when you add two vectors, you need to have a vector. So therefore, 0 has to be a vector. All right, that's the additive inverse property there. As the inverse of the opposite of a vector to the vector, you get 0. Now, those are mostly dealing with addition. You go back and do subtraction too if you wanted to, remembering they're just adding to it. Well, no, you may not have gotten there yet, sorry. All right, here's the multiplication and distributive type properties. If you have a number C that you're multiplying by the number D times a vector U, this is called a scalar multiple of D times U. That's the same as multiplying C times D and then multiplying that by D. In other words, if you have two scalars and a vector, they're in some senses sort of associative, okay? But you have to be careful with two scalars and a vector. Number 6, that's an associative property. They didn't say that, but it's sort of an associative property of two scalars and a vector. This is one that is a type of the distributive property. When you have two scalars being added, multiply that times a vector, that's the same as the first scalar times a vector plus the second scalar times a vector. It's sort of a distributive property of scalar multiplication over vector multiplication over scalar addition. Whereas number 7 is another kind of distributive property. If you have a scalar multiplied by sum of two vectors, which is a vector, that'll be the scalar times the first plus the scalar times the second. So that's the distributive property of scalar multiplication over vector addition. So it's slightly different there. And then the last of these properties, 1 times u, of course, is u. And since they said up here, u plus 0 is u, then 1 times u would be u. That's the multiplicative identity property. Why they didn't put that down here, I'm not sure. So I'll go on and write it in here too. Oh, man. Ooh. Okay. I think we're still in red, and this is red, so this is, the first of these is multiplicative. Identity property. The second of these is 0 times u is a 0 vector. And that's kind of the zero product principle in some senses. I'll write it down. It's not quite the same, but it's pretty close. Zero product principle or property. Okay. You don't have to have a name for that, but since I had the additive identity, I said, why not have a multiplicative identity?
Why did we put that?
What's that?
I didn't forget to put that in.
I don't know. I mean, it seems like it fits there perfectly, but it's in the book too, so they left it off. Why, I don't know. Okay, I think we talked about Emmy Noether right before we ended class last time. Okay, so I won't go into her again. They do show a proof here of the associative property of vector addition. Certainly a straightforward way to do it. In fact, many of these, you break it down into components. Since it's all in the plane, they only have 2 components. So you can show those pretty easily. A lot of them. Okay. Now, any set of vectors with accompanying set of scalars that satisfies the 8 properties listed there, in theorem 11.1, is a vector space. Okay, they're jumping right in the vector spaces. Okay. The 8 properties are the vector space axioms. Okay? Now this is the first time I've taught this chapter in this text, and it's pretty interesting. He's doing a little bit more than most other books I've taught from, calculus books. But he also has written a linear algebra book. We use his, and so I think that's why he's getting into that. So this theorem states that the set of vectors in the plane with the set of real numbers forms a vector space. Okay? And let me. All right, double the class size. No comments here. Oh, I forgot to put Mark on here. How did I overlook it? Okay. Comments here. So the bottom part of the alphabet's not doing awful. The top part's completely vacant. Okay. Now, so here's theorem 11.2. The length of a scalar multiple. Okay. I would be a little bit better if they put the word vector at the end, but it's okay. Let V be a vector and let C be a scalar. Then, what is the magnitude or the length of the product of C times V? Well, you might think that would be C times the product of V, of the magnitude of V. Not quite, because C could be negative, and your magnitudes are always positive, so therefore we have to put absolute value of C, okay, which is fine. So the absolute value bars are this, the magnitude bars are that, but they really relate to each other fairly closely in that neither can be negative, okay? One for vectors and one for scalars. Okay. Now, They do a little proof here too. I'll let you look at that if you'd like. And then let's move on. In many applications of vectors, it's useful to find a unit vector that has the same direction as the given vector. The next theorem gives a procedure for doing this. And this is pretty straightforward. I would almost think, even if you didn't think of the solution once you see it, you say, oh, of course, okay? If V is a non-zero vector, okay, you can't talk about a unit vector with a zero vector. It just doesn't work. All right, here is Davis, right? No, Preston, I'm sorry. I looked at the wrong name. By the way, that reminds me, I didn't finish marking my first class. Let me do that before I forget it. Okay. Okay, we'll see. All right. We're looking at theorem 11.3, unit vector in the direction of V. If V is a non-zero vector in the plane, okay, you cannot talk about a unit vector being in the same direction as zero vector because zero vector has no direction, so it has to be a non-zero vector. Then the vector U, now, let me just say this. Every time you see a U, that's not necessarily a unit vector, okay? So, in this case it is, but they quite often use U, V, and W as being generic vectors, and U is not always a unit vector. This one is. And that's, therefore, when I'm writing a vector that is a unit vector, I put a caret over the top, you know, the little, it looks like a rooftop. That's how I distinguish and remind myself this is a unit vector. Okay. So this one is a unit vector, but they don't have any special symbol for that. You want it in the vector U, which is the vector V, divided by the magnitude of V. That's going to be the a unit vector in that same direction as V. Now, for some reason, they then wrote this as 1 over magnitude of V times V. I think the reason they did this to make this look like it is a scalar, because the magnitude of vector is a scalar. It's a positive scalar. So this is going to be the vector. So you see, if V is a long vector, this is going to scale it down to 1, a vector of magnitude 1. If it's a little tiny one, this scales it up because you're dividing by a very small number. It scales it up to magnitude 1. So this unit vector has length 1, but the same direction of V, whatever direction V is. Okay? In this theorem, U is called the unit vector in the direction of V. There's tons of unit vectors out there. Just have magnitude 1 and point them any way you want to, and that's a unit vector. Okay? On the plane, you know, you can do it that way. Okay. The process of multiplying V, the vector V, by 1 over its magnitude to get a unit vector is called the normalization of V. Now, I guess the word normal in everyday language means kind of average, or, you know, the expected, you know, that kind of stuff. Okay? When you see normal a lot in math, a lot of the times in math, normalization means reduced to 1. Okay? That's what it means. It doesn't mean the regular expected. It means reduced to 1. So the magnitude is reduced to 1. Okay. Generally, the length of the sum of two vectors is not equal to the sum of their lengths. Okay? If this is vector U, you're adding to vector V, the sum of those two vectors is not the same as the magnitude of the sum of the two vectors is not the sum of the magnitudes of the two vectors in general. It may be in very special circumstances. What circumstance would that be true? that the sum of the magnitude will be the magnitude of the sum. Only one situation. If vector v was in the same line of u, in the same direction of u, then u plus v, the length of u plus the length of v would be the length of u plus v. Any other angle, wherever it is, it's not. Even if it's collinear but in the opposite direction, then it's definitely short. Okay? So, generally, I want to state this even stronger. The length of the sum of two vectors is less than or equal to the sum of their lengths. Always. It's not equal to, it's less than or equal to. Okay? Generally, it's not equal to. Okay? Now, I think we've seen that. And this, by the way, leads to what they call the triangle inequality, that magnitude of u plus magnitude of v is less than or equal to the magnitude of v plus v. I think they express it here, okay? So with u and v as two sides of the triangle, the length of the third side, magnitude of u plus v, and the lengths of the other two sides, the magnitude of u plus v is always less than or equal to the magnitude of u plus magnitude of v. Oh, I'm back. Oh, by the way, folks, I didn't say this when everybody came in, but let me say it now. Before anybody has to leave today, let me know a few minutes before so I can go through the schedule for the end of the how we're going to wrap things up. Okay? Now, and as I was saying before, that equal sign there only occurs when u and v are collinear and have the same, they're collinear in the same direction. Okay? That result is called the triangle inequality for vectors. Okay? This is on page, by the way, 756. No. I'm sorry. We skipped example 4. That was the top of 757, but I missed example 4. So let's back up and do example 4. Okay, we'll do it here. Well, let me get my pen back. I was using red before, but I don't need it now. Find a unit vector in the direction of v. Here's vector v. I don't draw bold, so I put the arrow over vectors. Vector v is, the best way to express a vector is in component notation, -2, 5. That's in a plane. That's supposed to be an angle bracket. It's not a very pretty one. And verify that it has a length of 1. So how do we find a unit vector in that direction? Pretty straightforward. How do we do that? Anybody? Okay. Let me scroll forward a little bit. That right there. What do we do? Find the magnitude of v. And how do we find the magnitude of v? Remember that? Anybody? Second, square root of. Second. Basically comes from good old Pythagorean theorem, doesn't it? Let's just draw this vector, okay? It's -2, +5. Okay, somewhere up here, right? And the magnitude of that vector, that's the length of that vector, is, this length here is 2, this length here is 5, and what's that length of the good old hypotenuse? Either one of those two that's the hypotenuse for. tell me you don't know Pythagoras. Square root of what? Second? Okay, it's the square root of negative 2 squared plus 5 squared. Right? Distance formula too. Same thing. From Pythagorean theorem. The 2 squared plus 5 squared is 8 squared, right? Yeah. Okay. Well, then the square root is okay. So this will be the square root of 4 plus 25 is square root of 29. And you always use the principal square root because it's positive magnitude. So we got the magnitude. How do we find the unit vector that is in the same direction as v? I scrolled ahead before. Right there. You see? What? Take the vector v and divide by its magnitude. Okay? So that would be the unit vector. Now I write a unit vector that way with a caret on top. Okay? Not a cherry. Okay? And that would be 1 over root 29 times the vector v. Well, the vector v is negative 2, 5. Okay? Or, probably a little bit neater way of writing that is the vector negative 2 over root 29, comma 5 over root 29. Sounds like the highway, doesn't it? Okay? Now, the second part of their question said, verify that it has length 1. How do we verify the length of that? In other words, we're looking at the magnitude of that unit vector. What would that be? Help me. And here's Bailey. I know you're in here. There you are. All right. Now, again, before anybody has to leave today, be sure you let me know so I can, with a few minutes to spare, so I can go over what we need to do at the end of the term, or the end of the term. Okay? I'm not going to say it every time someone comes in because that would be repeating the same thing over and over and over. So just remind me before the first person has to leave, I'll take that opportunity to go over that. So what is that? Verifying magnitude of u. What is the magnitude of a vector? Nicoma started us last time. Square root of negative 2 over root 29 squared plus 5 over root 29 squared, right? Okay, when I square a negative, it becomes positive, so it'll be the square root of. And what's 2 squared? 4. What's root 29 squared? 29. Plus 5 squared is? 25. Over root 29 squared is? 29. And what's 4 plus 25? 29 29ths is 1. Magnitude, square root of 1 is 1. So the magnitude of this is indeed 1. So we verified that is a unit vector. Okay? Because we took the original vector, divided by its magnitude, it's got to have a magnitude of 1. Okay? And that's it. So that unit vector would be one that would be down here, something like that. Okay? Maybe a little bit longer. That would be the unit vector. It's the same direction, but scaled, in this case, down to 1. Okay. And that's what they did in, let's see how they don't do this. So let's go over, that's example 4. So let's go back to where we were before I realized we'd skipped 4. And we had talked about this and that, triangle inequality. Now let's look at standard unit vectors. What do you think they mean by that? Remember I said a unit vector in the plane is any vector that has length 1. Whichever way it's pointing, it all has length 1. Well, sure, we want to get a little more less random unit vectors. In other words, standard unit vectors. Anyone know what these are already? You do, you probably just don't realize it. The unit vectors 1, 0 and 0, 1. Aren't those unit vectors? Magnitude 1. Square root of 1 squared plus 0 squared is 1. Square root of 0 squared plus 1 squared is 1. So those are unit vectors. These are called the standard unit vectors in the plane and are denoted by I and J. When you go to 3 space, there will also be a K, okay? But it'll be 3 components, not 2, okay? So that's your I vector. That's the vector. I always call it the horizontal component of the vector in the I direction, okay? And the J component is the vertical component, if you draw them like this. Orient other ways, and they won't be horizontal and vertical. Those are the 2 unit vectors. And when I write them, I usually put the cap on them. That way you know I'm talking about a unit vector. Because guess what? If you write the letter I, you might say, we're talking about imaginary numbers. No, we're not. Not in vector stuff. The I stands for the unit vector in the X direction. And J is the unit vector in the Y direction. Okay? These vectors can be used to replace any vector uniquely as follows. Okay? This is our good old component notation, which is the most concise, nicest, most pleasant way to write a vector. Vector V is a horizontal component, comma, vertical component inside the angle brackets. Okay? Or you can express that as the horizontal component, comma 0, plus the 0, comma the vertical component. That's doing this component plus this component, that gives you that component. That gives you vector V as well. Or you could pull out the V1 here and do times 1, 0, pull out the V2 here, and that would be times 0, 1. Well, guess what 1, 0 is? What is 1, 0? Vector 1, 0. I. Okay? And vector 0, 1 is J. Okay? So this is V1I plus V2J. In fact, back when I was, the earliest I can remember doing vectors, we didn't have this form. I don't ever remember seeing this form of vector notation with the angle brackets. When we did component notation, this is how we did it, I and J. Okay? It says the same thing. This is just a more concise notation. But that's where the angle brackets are so neat, because that means that's a vector. Like I said, this author, I also teach a linear algebra course from same author, and he put vectors in parentheses. And I do not know why. Okay? I also teach his pre-calculus text, and he puts them in angle brackets there. So these angle brackets are pre-calculus, calculus, but he puts parentheses on linear algebra. I do not know why. So the vector V, VI, V1I plus V2J is called a linear combination of the 2 unit vectors I and J. By the way, I and J, since they're perpendicular from each other, they are what we call linearly independent. So not only is this a linear combination of the 2, it's a linearly independent combination of the 2. The scalars V1 and V2, when they're written, not bolded, well, they're seldom, they're always written, are called the horizontal and vertical components of V, which is exactly what we call them there too. Okay? The V1 is the component in the x direction, v2 component in the y direction. So horizontal and vertical components. Okay. All right. Now, here's example 5. Let u be a vector with initial point, and these are, notice, parentheses, these are points, 2, -5, and terminal point, -1, 3. Okay? And it says let v be the vector 2i minus j. Right? Each vector is a linear combination of I and j. Okay, so let u be the vector initial point that and terminal point that. Let v be 2i minus 3j. Write each vector following as a linear combination of I and j. So let's first write a, which is u, as a linear combination of I and j. Anyone want to tell me what the coordinates, components for vector u is? Okay, are. How do we do components of that? If you're given the initial point and the terminal point, how do you get the components? This was last week, or maybe even Monday. You remember? You sure should. The x components are always terminal minus initial of the x value. So that would be -1 terminal minus 2 initial. Okay, that'll be the first component, and the second component is the y component. The vertical component would be 3 minus a -5. Okay, so that would be -3 comma, second? Okay, it's 3 minus a -5. Minus a minus makes a plus. 8. Okay? Alright. So that is vector u in component notation. Now write it as a linear combination of I and j, which is a piece of cake to do. What would that be? This is the horizontal component. This is the vertical component. This is the component in the x direction. That's the component of the y direction. So what would this be in ij notation? Okay. If you have it in this component notation, which we do, this puts it in ij notation. Right? And what will that be? Wait, where is it? There it is. What would that be? Second? -3i plus 8j. See, I put carets over on the reminder. Those are unit vectors. Okay. So we've done the A part. Took a while, didn't it? Let's do the B part. W is equal to 2u minus 3v. Now, to me, the easiest way to do this is in component notation. That would be 2 times, what's the component notation of u? Second? -3, 8. Oops. Forgot to do my angle bracket. Minus 3 times, and what's the component notation for v? Say again? 2. Okay, that's it. Okay, if we had written in that notation, then I would have done 2 times -3i plus 8j minus 3 times 2i minus j. Now, if you're figure out which way you're going to do them and write it. If I was doing in component notation, I would have written this as 2, -1, right?
Yeah.
Either way you want to do it, it's fine. They say the same thing. What does that give us? To me, it's just a little easier to do that first one. What would that give you? -6 would be the x component. 16 would be the y component. And do you want to do a plus or a minus? I don't care. Second? Plus. I like that too. And then that would be a -6. If you're doing the plus, then pull that in. -6. I'm sorry? Yeah. Making fun of my writing, aren't you? Okay. 3, right? Okay, and then can you do the last step? Please say yes. Yes. Whoa. You're adding. -12, comma, 19. All right, I feel like a dentist, but y'all did well, okay? Now, that's in component notation. It said write that as a linear combination of I and j, and what would that be? You write it in -12i plus, no, yeah. You see, in this notation, you write it plus or minus, okay? Plus 19j. Okay, that's it. Okay, the first one was -3i plus 8j, and the second one is -12i plus 19j. Now, since they wanted it in that notation anyway, perhaps this one would have been better to do it this way. And it does the same way. That would be -6i plus 16j minus 6i plus 3j, and then you basically combine like terms. -12i, I, okay, goodness gracious, plus 19j. That would have been a little easier to do it that way, using the linear combinations from the very beginning. Either way works. Does that make sense? Any questions? That's our rendition of example 5. Let's see how they do it. So I'll erase all my scratch, and let's see how they proceed. So, they start the same way we did. They start by doing the vector u in terms of the components that you get from the coordinates of the points, okay? Which would be, and they call it q and p, where p is the initial point and q is the terminal point. So q1 minus p1, that was our -1 minus the 2, comma, 3 minus the minus side. And that would have given us -1, -2, comma, 3 minus the minus 5. That gives us -3, 8, exactly like we got. And then to get it in as a linear combination of I and j, that would be -3i plus 8j. Everybody see it? Understand? Okay. Now, let's do the B part. They tell us that W is 2u minus 3v, and they did it the way Angel was suggesting, and it actually worked out simply there because this is the form you wanted in the beginning. At the end was 2 times your -3i plus aj minus 3 times the v, which you already had in that form, 2i minus j. And that gives you minus 6i plus 16j minus 6i plus j. And that gives you negative 12i plus 19j, exactly like we got. Now, I was a little hesitant when I was doing it because I wanted to make sure they didn't change. When you write it in the ij notation, there's no reason to put angle brackets anymore. That shows it's a vector. So then parentheses are appropriate there. When you write it in component notation, you've got to put the angle brackets to indicate that is a vector. But when you have the ij notation, it's fully obvious. And all right, I'm sorry. Did this morning about midway through the class. I just started clogging up like crazy. Of course, in that class I started with sneezing like I couldn't quit, and then finally just had to stop and go clear my head. All right, I think we're through with what we have there. Let's move on to, this is just, well, I thought they were going to show this, the figure 1111, but they're not. It's a little bizarre that they skipped this. Okay. Do most of you do not have books here, right? Unless it's an ebook. Okay. So I think I'll order to do something with this. Let me try to draw this. If u is a unit vector and theta is an angle measured counterclockwise from the positive x-axis to that vector u, then the terminal point of u lies on the unit circle, okay, because u, remember, is a unit vector, meaning a radius 1, length 1, that would make it describe a unit circle whose radius is 1. So here's another way you can write then the terminal point of u, okay. Okay. They just sort of pop this out there, but it's absolutely true. That unit vector, generic unit vector, can be written this way. Cosine theta, sine theta. Okay? Well, hell, I think I recognize this guy. I can't remember where from, but I've seen him somewhere before. There you are. Okay. They just sort of land this on you, okay? If u is a unit vector, theta is the angle measured counterclockwise from the positive x-axis to that vector u, wherever that happens to be, whichever way it happens to be pointing, then the terminal point u lies on the unit circle. Why? Because that vector u, you rotated about the origin, it has radius 1, you've just described a unit circle. Okay? So that's radius 1, and any unit vector can be represented by, because it has a radius of 1 on that circle, and it's represented by its, if this is its angle theta, then the x component of that vector is 1 times the cosine of theta, and the y component is 1 times the sine of theta. Okay? So this is how we write that. Now, if I were to ask you to prove that is indeed a unit vector, how would you do it? Verify that's a unit vector. We did it a couple times already today. How do we do that? Anybody? Say again? See, those aren't numbers. We're used to having numbers there. This is a function, trig function, no less. So how would we verify that is indeed a unit vector? It has to be a unit vector. What's the magnitude of that? How many times have we done it today? Second, square root of cosine squared plus sine squared. But what is cosine squared plus sine squared? Second is the Pythagorean identity. And I'm going to have to talk with your trig teacher if I don't get an answer real soon. I was a trig teacher. What's sine squared plus cosine squared? 1. Any angle in the world. So sure enough, this is indeed a unit vector, because cosine squared plus sine squared is equal to 1, so the square root is 1. That's got to be a unit vector. So whatever the angle is here, whichever way that unit vector is pointing, the sine squared plus its coordinates, so sine squared sine comma cosine. And let's make sure we got it in the right order too, because cosine is related to the adjacent side, so that's the horizontal axis, and sine is related to the vertical side, which is your, the y-axis. Okay, so yeah, that looks like that would be fine. Starts at 1, 0, because when theta is 0, the cosine is 1, the sine is 0. And it moves around in a positive direction here, because cosine is positive in the first quadrant. So as sine positive in the first quadrant, it moves up here, cosine decreasing in length, sine increasing in length until you get the pi halves, and cosine of pi halves is 0, sine of pi halves is 1. There you are, right in the right place. And you keep on going around into the second quadrant, cosine becomes negative, the sine stays positive, decreases here, as the sine does, cosine gets more and more negative, so they're both decreasing until you get to pi. Cosine of pi is negative 1, and sine of pi is 0 again. So there you are, negative 1, 0. Keep on going around. You see, you trace out the entire unit circle by that vector. Rotating that vector around with from 0 to 2 pi. Okay? Now, so another way to write that, if I said write it in as a linear combination of I and j, what would you write that as? Linear combination of I and j. Help me, somebody. Anybody? Linear combination of I and j. Cosine theta I plus sine theta j. Even though those aren't numbers, it works for this because of that relationship. Okay? So that's how we write that. That's the unit vector u. Moreover, it follows that any other non-zero vector v making the same angle theta with the positive x-axis has the same direction of those u's, and so you can write v, any old vector v, not necessarily a unit vector v, would be the magnitude of v times, and they write it both ways, don't they? Yeah. Cosine theta, comma, sine theta. Okay, which would also be written as magnitude of v times the cosine theta I plus magnitude of v sine theta j. Okay. Goodness gracious, I'm having trouble following. Okay. Because this is the unit vector in the same direction, multiply it by its magnitude of v, and you get the v vector. Because remember, v vector divided by magnitude of v gives you that unit vector. So, using it both ways. Now, I think they skip example 6. Let me check and see. Yeah. So let's do example 6. All right. Using that same stuff here, but I don't have room to keep it on the screen. All right. Find a unit vector in the direct, oh wait, here's this. The vector v has magnitude of 3, okay? That means magnitude of vector v is equal to 3, okay? And makes an angle of 30 degrees, theta equal 30 degrees, which is also, anyone tell me what that is in radian notation? 30 degrees. Pi 6, excellent, okay? Pi 6, okay? With the positive x-axis, and that's done counterclockwise, okay? So we know exactly where that is, okay? That would be something about like, maybe I got it a little too far. That's about 30 degrees or pi 6 radians, okay? Write v as a linear combination of the unit vectors I and j. Can you do that? V is equal to, it's a linear combination of the unit vectors I and j from what we just did. Okay, anyone do it? Okay. Cosine theta I plus sine theta j. Now, what would that give you? If that's all there is, that's a unit vector, because cosine squared plus sine squared is 1. But this says this vector. Is this vector v a unit vector? No, its magnitude is 3. So it's not a unit vector, it couldn't be. To be a unit vector, the magnitude has to be 1. So we want to express this vector as some linear combination of those. And I'll tell you, what you got so far is okay so far, you just don't have it complete. That has magnitude 1. That says it needs to have magnitude 3. So what would you do? Pretty simple. Say again? Plug in what? Okay, yeah, we're going to do that. You're absolutely right. But let's set it up so this is going to be a true statement. This is not a true statement the way it is now. Because this says magnitude of V is 3. I know the magnitude of that is 1. Pretty easy to do. Multiply it by 3, don't we? Okay? So, that would be 3 times cosine, and what did you say? Plug in 30 degrees. Do you prefer 30 or pi 6? I don't care. You tell me. Huh? Pi 6, okay. Pi 6 I plus 3 times sine of pi 6 j. Well, what is cosine of pi 6? Anyone remember? Nope, cosine is. Not cosine. Cosine is? Second? Root 3 over 2. So that would be 3 times root 3 over 2 I plus 3 times, what was sine? 1/2. Okay, j. So this would be 3 root 3 over 2I plus 3/2 j. All right, that's what your V is. 3 root 3 over 2I plus root 3, or 3/2 j. All right, good deal. All right, now we're ready for the next one. All right, now, vectors have many applications in physics and engineering. Some of you already had your physics, right? Okay, others may not have. And engineering, and most of you are going that way, right? One of these examples is force. Force is a vector. You don't have a force that doesn't have a direction on it. So force is a vector quantity. In fact, it's almost easier to name the things that are not vectors. Mass, time, energy. Maybe something else, but those are the things that are not vectors. Oh, distance, not a vector. Okay? Displacement, though, is a vector, because that's a distance but in a certain direction. Velocity, a vector. Speed is a scalar. Acceleration is a vector. Force is a vector. Momentum is a vector. And Terrell is, no, he's just here. Okay. All right. So many things are vectors. One of these is force. A vector can be used to represent force because force has both magnitude and direction. If two or more forces are acting on an object, then the resultant force on the object is the vector sum, not the scalar sum, that doesn't even make sense, of the vector forces. Okay, so it's a vector sum. Now, let me give you a dumb example, and this was a true one. When we first moved to the house where we currently live, we were coming from a place that had basically no trees on the whole lot, but it was a very small lot. We got a little bit of shade from the big tree that one neighbor had, and then back in the back corner, we sort of right on the border was another really scrub tree. We seldom were able to use that. But we moved to a lot that was a really nice sized lot with lots of trees on it. In fact, too many trees on it, in fact, because there were these big old oak trees and not quite as big as oak trees, and then two huge pine trees and hickory, hackberries, and other things like this. So then there were two other little crooked pine trees trying to find a way to the light because they were underneath all these oak trees and the maple tree and all these other trees. And two pecan trees, walnut trees, I mean, there's just trees. And these two really crooked, ugly little pine trees were trying to find a way to the light. They've grown really crooked. Okay? So we said, we really need to take those down. And so my father-in-law came down with his chainsaw and brought with him my brother-in-law, and Corbin's here. So they came down to help us take down the pine trees. And he also brought with him a long rope And what we did, because our house was there, we had plants there, we had other things there, we wanted to minimize damage when the pine tree came down. It wasn't a huge pine tree, but it was very, very tall. So we threw the rope up as high as we could and got one branch that was somewhere way up there. You know, when a tree doesn't have much light, it doesn't have any branches down below, all the branches are up top. And that's what the case was here. It took us several times, but we got it up, wrapped around a branch. So my father-in-law was going to use a chainsaw, and my brother-in-law and I were going to pull on the tree to get it to come in the direction we wanted it to fall. Now, the optimal way to get the most force on that tree would be if we pulled in exactly the same direction that we wanted the tree to fall. What's wrong with that picture? It's going to fall right on top of us if we were successful, right? We didn't want that to happen. So we separated ourselves, but still pulled in that general direction. Now, we weren't optimizing the force because I was pulling this way, he was pulling that way. Because forces are vector quantities, we had components of force. For mine was this way, so it had a component in this direction and the direction we wanted to fall. He had a component in that direction and the direction it wanted to fall. So basically, these two components of the force canceled each other out, but these two added together, and we got the tree to fall in the direction we wanted without it landing on top of us. That was the objective achieved. Okay? So that's the same type of thing here. You want a resultant force, but you may have conditions on that. So here we have two tugboats pushing on a big boat. Are you going? Leaving?
No.
Oh, okay. Okay, two tugboats are pushing on. And by the way, no, I haven't said this since everybody came in. I held off all announcements and stuff like that until the maximum number of people get here. And how I'm going to judge that is before the first person has to leave. So if you have to leave a little early, stop me a few minutes so I can go over how we're going to wrap up the term. Okay? If you don't stay till the end, we'll do that right at the end. Hopefully more people come in. Okay, so two tugboats are pushing an ocean liner. These are either big tugs or a small ocean liner, I don't know which. As shown in this figure, each boat is exerting a force of 400 pounds. What is the resultant force on the ocean liner? Okay? Now, here's the angle with the horizontal. That's a minus 20 degrees. Here's the angle with the horizontal of this tug, a plus 20 degrees. Okay? So to get the net force on the ocean liner, and they each are pushing with a force of 400 pounds. Frankly, sounds pretty small to be pushing an ocean liner, but you know, that's, I guess, all they got. Okay? Now, we're not going to talk about accelerations here, we're just talking about forces. Okay. Now, I hope it's pretty obvious to you. Well, yeah, hopefully it is. If the magnitude of the force is 400 pounds on tug, let's do tug one down here. Tug one down here. Magnitude of the force is 400 pounds, but it's in that direction. Okay? So that gives you a horizontal component of the force of 400 times the cosine of 20 degrees. Because you see, cosine is adjacent over hypotenuse. This is your hypotenuse, 400. This is the adjacent. So cosine 20 is adjacent over hypotenuse. So the thing we're looking for over hypotenuse, multiply both sides by hypotenuse, you have 400 times cosine 20 is equal to the horizontal component. The vertical component here for this tug is 400, the magnitude of the force, the hypotenuse, times the sine of 20 degrees. That gives you this component. Up here, this one with a minus 20, its horizontal component is going to be 400 times the cosine of negative 20 degrees, whereas the sine component, the vertical component, is going to be 400 times the sine of negative 20 degrees. Now, I need you to help me remember something. how is cosine 20 and cosine negative 20 related? Do you remember that? Cosine is one type of function and sine is another kind. Remember, did y'all talk about this in trig? Even and odd functions. Did you do that? You better not say no, okay? Because I know the trig course you have. You remember? Cosine, think about how a cosine function looks, okay? To me, graphs are useful, okay? Think about a cosine function. Okay, it doesn't go down, okay? It's like that. So if you go minus x or plus x, you get to the same, if you drew it right, you get to the same value. So cosine of negative x is the same as cosine of x because it's an even function. Remember that? Whereas sine function, if you go minus x, it's negative. If you go positive x, it's positive. Same value, but opposite signs. So the sine is an odd function. Okay? So since cosine minus 20 is the same as cosine positive 20, then you add those two together. So your x component on the tug will be 400 times 2 times the cosine of, I should have put the 2 in front, of 20 degrees. Because cosine of minus 20 is the same as cosine of 20. Okay? And the sine, on the other hand, since those are opposite from each other, the sine of minus 20 is opposite the sine of 20, so these two cancel out. This is going to be a negative value, this is going to be a positive value. They're exactly the same size, but in opposite directions, so therefore they cancel out. And you can see that in the graph. One's up, one's down, they add to 0. So the resultant force on the ocean liner would be 800 times the cosine of 20 degrees. And somebody can punch that in a calculator and see what you get. Anyone got a calculator? 800 times the cosine of 20. It's not that hard. Anybody? $800 times the cosine of 20.
326.46.
Say that again.
326.46.
That sounds,
I got 751.
okay, that sounds better. Okay, I think you must be in radian mode.
Oh,
Yeah.
let me check this.
Check what mode you're in. What do you have?
751.6. There it is.
That sounds reasonable. 751.75? Is that what you said?
Yeah.
Okay, so let's call that 752 pounds. And frankly, if you're pushing with 752 pounds on an ocean liner, good luck. I mean, you're going to move it, but it's going to be awfully slow. Okay, I think. I've never pushed on an ocean liner, so I don't know for sure. Okay, they got 752 pounds. Okay. They did the I and J. You can do the I and J if you want to. Okay. Oh, here they have it. Using figure 1112, you can represent the forces exerted by the first and second tugs as force of the first tug, 400 times cosine 20, comma, sine 20, vector. Okay? That's what we did. Magnitude times the unit vector. Okay? That would be 400 cosine 20i plus 400 sine 20j. And F2 would be 400 cosine negative 20, comma, sine negative 20, which is 400 cosine 20. Now, here's what they did. because the cosine of negative u is the same as cosine of u, they just changed that to 20. But the sine of negative u is the opposite of the sine, so they made this a minus 400 sine 20. Okay? Now, if you add those two together vectorially, which means add the I components and add the j components, I components add to be 800. Okay, there we have it. That would be 400 cosine 20. Okay, spread it out there. It's fine. That's F1 and F2. And that would be 800 cosine 20i and 400 sine 20j minus 400 sine 20j adds to 0. So this is 800 cosine 20i. That's about 752i. And everything was measured in pounds, so that would be pounds. Okay. So the resultant force on the ocean liner is approximately 752 pounds in the direction of the positive x-axis. Okay. Now, any of you going into civil engineering? Okay. If you were, you'd be doing a bit of surveying, I bet. Okay? Most other engineers, I don't think, do too much of that. But in surveying and in navigation, so if you're going in nautical engineering, which I know how to use, the bearing is a direction that measures the acute angle that a path or a line of sight makes with a fixed north-south line. Always the acute angle from a fixed north-south line. Now, in air navigation, bearings are measured in degrees clockwise from north, okay? Yeah, just air navigation, clockwise from north. Actually, nautical navigation as well, but we'll let them think otherwise. Whoa! That was it. That's all she said, okay? So let's do example 8. And example 8, by the way, is at larsoncalculus.com for an interactive version of this type of plane. So an airplane is traveling in a fixed altitude, at a fixed altitude, with negligible wind factor. Thank you so much. The airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. Okay? So looking down on the airplane from above, with north being that way, okay, the airplane is traveling at a bearing of 330 degrees. Well, that's 30 degrees short of 360 degrees, right? So this is 30 degrees short of 360. Now, in other instances, we would call that north 30 degrees west, okay? Because you have to indicate whether you're looking north or looking west, south. And you're going to keep acute angles, so it's going to be one or the other. So north 30 degrees west. You're going west of north by 30 degrees, okay? Okay. As shown in this figure, okay? Theirs isn't quite as pretty as mine, but you got it, okay. Now, what they put is they put this angle. Well, that angle is 90 plus 30, 120 degrees, and that's from our standard way of doing it. Aeronaut does 330 clockwise. That's what they told us, which is north 30 west in bearings, and it's 120 according to the way we've been doing things. So however you do it, you decide, and then don't mix them up too badly. And by the way, this vector here is the magnitude of this, the velocity is 500 miles per hour. I think it was, wasn't it? Yeah. Now, as the plane reaches a certain point, it encounters wind with a velocity of 70 miles per hour in the direction north 45 east. So here comes a wind north 45 east. So that would be about here. So here is your wind going in this direction. That's 45 degrees. And 70 mile per hour wind. So this length here is 70 miles per hour. Okay. what is the resultant speed and direction of the airplane? Okay? Once the wind starts. Okay? So what we have here is a vector in this direction. That's I'm going to call it the plane velocity, is going to be 500 times, and I think they're going to use 120, so we'll use 120, cosine 120i plus sine 120j. Now these are degrees. Okay. I really don't like using that, but I will. The wind speed, on the other hand, is going to be 70. Now, if we are using this down here, we're going to have to use it here too. Well, if this is, let me draw this over here, north 45 east, this is east, then what is that angle going to be? If this is 45 here, what is this angle? 45 also. So that's going to be 45 degrees from the horizontal. So this will be cosine 45 degrees I plus sine 45 degrees J. Okay. And you want the resultant, so you just add those up. Okay. So 500 cosine 120 plus 70 cosine 45. Okay. That's going to be the I component, the X component, the horizontal component of the resulting. Wait, wrong thing. Okay. Drop my one there. Okay. All right. And the Y component is going to be 500 sine of 120 degrees plus 70 sine of 45 degrees. Okay. Now, you can almost do this without a calculator. It'll help to use a calculator. Because 120, the sine of 120, that's in the second quadrant, only you would use its reference angle here to be 60, and the cosine of 60 would be 1/2, but that's a negative 1/2 because the cosine is negative. So this will be negative 250. 1/2 of 500 is 250, and 70 times the cosine of 45, that's going to be a positive. That would be 70 times root 2 over 2, because that's the cosine of 45. So that would be 35 root 2. That's going to be your I component. Your J component is going to be 250 times root 3, because the sine of 60 degrees is square root of 3 over 2. The 2 factors that down, plus 70 times root 2 over 2, so that's 35 root 2. Okay, so now you use your calculator. Negative 250 plus 35 root 2, that's your X component. Someone do that? Negative 250 plus 35 root 2. Anybody? Negative 250 plus 35 root 2. Negative 250 plus 35 root 2. To what? Negative Negative 200 point what? 0.50. Let's call that 201, okay? And your y component is going to be 250 root 3 plus 35 root 2. $482? Is that what you said, 482? Okay. That's going to be the components in that direction. What did they ask for? What is the resultant speed and direction of the airplane? So to get the speed, how do we get speed? Anyone remember what speed is? The magnitude of the velocity, right? Which is, how do you get magnitude of a vector? We've only done it about 4 times today. Second, square root of. So the speed will be the square root of negative 201 squared plus 482 squared. All right. Now, how do we get, and someone punch that in and see what your speed is. Yeah. 522? Okay. They got 522.5. I don't know where they got the extra thing, but so that's 522 miles per hour. Okay, miles per hour. Now the direction. How do we go about getting the direction of that? Okay, let me at least sort of draw in what I think that might represent. Okay, that would be minus 200 with a positive 400. It's going to be something like that. I don't know if that's exact. Minus 200, positive 400. Something, say, up there. How do you get that direction? Second? Yes, that's it, exactly. The tangent, the inverse tangent of y over x, 482 over negative 201. Okay? Anyone do that with your calculator? Guarantee you're going to get a wrong answer, but it's usable. Inverse tangent of 482 over negative 201. Anybody? The inverse tangent of 482 divided by negative 201. Right there. Inverse tangent 482 over negative 201. Okay, say that again. Point what to? Point 82? Is that what you said? Oh, 67.72? 32. I can't hear. Okay. So, I guarantee you that's the wrong answer. Why? Negative 67.32 is down this way, isn't it? We know the plane's going that way because it's negative 201, positive 482. So how do we reconcile that? Add 182. Because remember, the inverse tangent is only defined from negative 90 to positive 90. So you're going to have to get an angle there. We're over here. It's not defined there. So when you get an angle here, and you know it's the wrong direction, add 180 to it. So add 180 to negative 67.32. What do you get? somebody. Not that hard.
47.
Second?
247.
Add 180 to negative 6732. It's not negative. You're adding 180 to negative 67.32. A positive 180 plus 67.32. Aha! All right, I think we got it now. That's going to be what? 112.27. Let's just leave it as about 112. I don't think we can get more. They probably rounded. They said 112.6. Okay. So the plane, speed of 522 or so, and with an angle of 112.6. Now that's not done the way they usually do wind bearing, but that's how the book gave it. So we're okay with it, right? So homework exercises here, any of the, well, do number 3, and it's at calcchat.com. Do either 5 or 7 or both. Both of those are at CalcChat, 5's at CalcView. Do any of the odds 9 through 15, they're all at CalcChat, 11's at CalcView. Do number 17, it's at calcchat.com. Do any of the odds 19 through 23, they're all at CalcChat, 21's at CalcView. Do 25, it's at CalcChat. Do 27, it's both at CalcChat and CalcView. Do any of the odds 29 to 33, they're all at CalcChat, none of them are at CalcView. Do either 35 or 37 or both, they're both at CalcChat, 35's at CalcView. Do either 39 or 41, they're both at CalcChat, neither are at CalcView. Do 43, it's at CalcChat, not at CalcView. Do any of the odds 45 to 47, either 45 or 47, they're both at CalcChat, 47's at CalcView. Do either 49 or 51, they're both at CalcChat, 49's at CalcView. Do either 53 or 55, they're both at CalcChat. Then exploring concepts, if you want to try 57 and or 59, I assume they're both at CalcChat. I would look first before I got too deep into it. And then any of the odds 61 through 65, they're all at CalcChat, none of them are at CalcView. Either 67 or 71, they're both at CalcChat, neither are at CalcView. 73 at CalcChat, not at CalcView. And 75, I would say either 75 or 77, they're both at CalcChat, neither are at CalcView. Any of the odds, we'll do 79, sorry, it's at CalcChat, not at CalcView. And then 87 is a decent problem. 80, goodness gracious, I can't talk. I'd say you choose 81 or 83. 81 is projectile motion, 83 is navigation, like we just did. All right. Do any of the odds 85 to 93, they should all be at CalcChat. If you want to do a proof number 95, and if you want to do a couple more, 97, 99, you can try those as well. That's up to you. All right, let's move on to 11.2. Any questions on 11.1? Okay. 11.2. Y'all doing okay? No one needs a break or something? I mean, this is a reasonable break point, but we don't have to take one if you don't want to. What you think? Keep trucking? Huh? Okay, let's take a quick break. I'm going to put this on hold. All right, let's get started on 11.2. We're still in vectors, Chapter 11, Vectors and Geometry of Space. So far, we've been talking mostly about the vectors part. This part, we're going to talk about space coordinates and vectors in space. Now, if you notice, before, we were basically two-dimensional vectors. We're definitely in the plane. Now we're going to be three-dimensional vectors because you're in space. Okay? So let's understand the three-dimensional rectangular coordinate system. That'll be our first objective, and then we'll analyze vectors in space. It's a pretty straightforward analogy from what we did in two-space or plane geometry. Yes, you call it that. But before extending the concept of vector in three dimensions, you must be able to identify points in a three-dimensional coordinate system. That's fine. You can construct this system by passing a z-axis perpendicular to both the x and y-axis at the origin, as shown here. Here's the problem, folks. We're drawing this on a planar board, a two-dimensional board. We're trying to draw three dimensions. And you can get decent representations of it, but when you look at it, unless you have something that's really clear like this, it's really, really hard to figure out exactly those things. Now, I like to wave my arms around here in the classroom. I like to use this corner back here as the origin, the floor down there, and then that's going to be my x-axis, that's the y-axis, and vertical is my z-axis. Now I can actually point to places in the first octant anyway and talk about their coordinates. But this enables us to do it in any of the octants. But the trouble is, you're in a two-dimensional drawing of a three-dimensional structure. So taken as pairs, the axes determine three coordinate planes. The xy plane, which is this one, x and y. The xz plane, which is the green, or I guess that's sort of greenish looking. And the yz plane, which is sort of the beige kind of looking. So the xy plane is the blue plane, xz plane is the green plane, and the yz plane is sort of the beige plane here. Now, that's still, none of those are on the plane of the board. They're all at weird angles with the plane of the board. So nothing quite seems like it makes sense. I mean, you can picture it as being, but you can't ever tell unless you really have things defined well. These three coordinate planes separate three space into 8 octants, and I already talked about this. Now, we don't have a decent way of numbering these, okay? We talk about the first octant as being positive, positive, positive. That's pretty clear. The rest of them, I don't think they have any numbering system for them. Here we talk about quadrants, 1, 2, 3, 4. You go counterclockwise from the positive, positive, and you have 4 quadrants. Here we only talk about the first quadrant, octant, and then the other 3, basically I would do by giving the signs, okay? So if this is the first octant, positive on x, positive on y, positive on z. Out front of the building here would be another octant that would be negative on x, positive on y, and positive z. Then that way, in front of the building, would be negative x, negative y, but positive z. Across over here in the fan room would be positive x, negative y, and positive z. Then you go down to the first floor and you get others. So we don't number them 1 through 8. We only talk about the first octant and then whatever the others are. Okay. Now, x is the directed distance from the yz plane to whatever point P you're talking about. And they give several of these points P's, and we'll get to them in a second. Y is the directed distance from the xz plane to whatever point you're talking about. Z is the directed distance from the xy plane to that point P. Several points are shown here. Okay. I don't care which one you start with. Let's just start with this one. So we're negative 2 on x, positive 3 on y, no, 5 on y. Okay. Each of these lines are my word. Not only have they drawn them, they've scaled them rather weirdly. Here is 1, 2, 3, 4, 5, 6, and X, positive and negative. But on Y, they've done 2, 4, 6, 8, okay? Negative 2, okay, strange. And then the Z is 1, 2, 3, 4, 5, 6. So you have to pay attention to the scaling. So negative 2 on X, positive 5 on Y, positive 4 on Z. Okay? So those first 2 points give you a coordinate in the XY plane, and then the fourth one, the third coordinate, is how far above that plane you are. Go over here to this point, you're positive in X, 2 units, negative in Y, 5 units, okay? And that's negative 2, 4, 5. So that's where you are in the XY plane, then go up 3 from there, and there you would be in that octave, whichever one that is. Come down to this point, again, positive 3 on X, positive 3 on Y, but negative 2 on Z, and that puts you down there, whatever octave that is. And over here, you're positive 1 on X, positive 6 on Y, neither going up or down in Z, so you're on the XY plane at that point there. Okay. Now, not meaning to cause you any grief or anything, but if you were to with the construction lines here, it's easy to see where they're talking about. If those construction lines weren't there, those would just be 4 points out here, and you really wouldn't be able to tell me anything about where that is. This one could be X, Y on the plane, but no, it's actually an X. See, if you came out far enough this way and then went that way, that would be XY with no Z component, okay? And the same, each of those could be done that way. This could be a YZ with no X component, okay? If that was your Y and then that was your Z, that would be it with no X component on it. So without some sort of construction line, it's really hard to tell what those. With construction line, you can draw any point you want to. Okay. Now, three-dimensional coordinate system can have either right-handed or left-handed orientation. To determine the orientation of the system, imagine you're standing at the origin with your arms pointing in the direction of the positive X and Y axes. Then, this is rather strange, the system is right-handed or left-handed depending on which hand points along the x-axis. In this text, we'll work exclusively with right-handed system. I was thinking, why in the world are they bringing up left-handed system? So basically it's saying, if you stand here in the corner, positive right is X to the right, positive Y to the left, straight up is positive, right-handed system. I don't usually think of it that way. I think of it this way. Point my fingers in the direction of the positive X-axis, curl them in the direction of positive Y. The thumb on my right hand will point in the positive Z direction. To me, that's right-handed. You know, shame that they don't use left, but never mind. Okay, many of the formulas established for two-dimensional coordinate systems can be extended to 3 dimensions. For example, to find the distance between 2 points in space, we use the Pythagorean theorem twice. Okay? Well, this may not be obvious that you would do it this way, but it is what you do. So you're a point P here, and again, you can't tell where this point is. It could be hanging up here, it could be back there somewhere, it could be anywhere. So what you do here is project Q down to the XY plane, or at least the same plane that P's on, and the Z1 plane, you might say. So this is X1, Y1, Z1, this is X1, x2, y2, z1, so you're on the same plane. The Pythagorean theorem here tells you the distance between these 2 points, if that's the same, is x2 minus x1 squared plus y2 minus y1 squared. That gives you this distance, and then that is one leg, there is the other leg, and here's your hypotenuse. So it's this thing squared, the total of that thing squared plus that thing squared. So just lose the square root here and add to it z2 minus z1 squared, and you get where they don't show you the answer there. Shoot. Okay, let me write in the answer for you. The D would then be, oh, let me get black or dark anyway. D would be the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That's a pretty ugly 2. Okay. That's how you do it. You just extend it one more unit out. Okay. There is your distance between any 2 points in space. 3 coordinate systems. Okay? Just logical extension from what it was in 2 space. All right. By doing this, okay, here's where they showed it to you. By doing this, you will obtain the formula for distance between 2 points, x1, y1, z1, and x2, y2, 0, 2, z2, and that would be square root of the difference in x squared plus the difference in y squared plus the difference in z squared. Now, for the distance formula, don't confuse this for other things, but for the distance formula, it doesn't matter which one you put list first or second, because you're doing a difference in squaring. Doing a difference in squaring it, doing a difference in squaring. Just make sure you keep your x's together, your y's together, your z's together. The difference between those. Be sure you're taking a difference. That's either going to be a positive number or a negative number. You square it, it's going to be the same. Okay? And then add those 3 positive numbers together, and take the square root of that positive number, and you'll get your distance. Always being a positive number. We don't go negative distances. Okay. Now, here's example 1. Should be pretty simple. Find the distance between these 2 points. You tell me how to do it. D is equal to what? Anybody? Between 2, negative 1, 3, and 1, 0, negative 2. What's the distance between those 2 points? Where do we start? Second? Okay, the square root. That's a great place to start. Then we do what? Okay, and what do you do with them? Second? Okay, yeah. And what would that give you? Okay. Negative 1. Okay. Okay, say that again. Okay, and what's that? Oh, well, you were going to square that? Is that what you were saying? Oh, yeah. Okay, got it. Okay. Okay, that squared. Okay. I got what you're saying now. I thought you had already done the subtraction. Okay. Okay. So you have a 1 minus 2 squared plus 0 second plus 1 squared. Minus a minus 1 is plus 1 squared. Plus okay, and that would be the square root of negative 1 squared plus 1 squared, negative 5 squared. And that would be 27. Okay? And square root of 27 you could write as 3 root 3 if you wanted to. Okay? That should be what we get. Yeah, and that's what they got to. Good for them. Okay? So let's see how they did it. And by the way, I just wanted to say this. Now this, again, only pertains to the distance formula. Later you have formulas, you have to be careful which one's initial, which one's final, and that kind of stuff. Here it doesn't matter. It's just the difference between these two. And to me, that difference is 1. 1 squared is 1. I can go straight to that. Difference between these two, 1. 1 squared is 1. And the difference between those two, that takes a little more thought. I would say 3 minus 2, which is 3 plus 2 is 5. Or you can say, it doesn't matter the order because you're squaring. Okay? But make sure that you do the same components at a time. So that's only the distance formula. You can ignore the other part. So let's clear this out of the way so we can see how they did it, which I think is very similar to what you did. The distance is 1 minus 2 squared plus 0 plus 1 squared plus a minus 2 minus 3 squared. And that would be the square root of 1 plus 1 plus 25, which is square root of 27, which is 3 root 3. All right, good deal. Now, there's, oh no, okay, a sphere with a center at 0, x0, y0, z0, somewhere out here, okay? Radius r is defined to be the set of all points x, y, z, such that the distance between x, y, z and the center, x0, y0, and z0, is r. Just that radius, whatever that is. So it's all the points that make that true. You can use the distance formula to find the standard equation of the sphere with radius r centered at x0, y0, z0. Okay? So basically what that says you do is this. The distance formula tells you the distance between that. That would be the square root of x minus x0 squared plus y minus y0 squared plus z minus z0 squared. And that distance is always equal to r. Okay? So if you know your r, you know your x0, y0, and z0, which usually they give you, then you can come up with that equation. Now, one way you can do it now is square both sides, and you have x minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to r squared. And that's a fairly standard way to express it. Another way is divide everything by r squared. Okay? And that would then give you this is equal to 1. Okay? And that's another fairly common way to express the equation for a sphere. Now, I don't know which one they're calling standard. Let's see if they give it to us. And you can take that one more step, I realized, as x minus x0 over r squared plus y minus y0 over r squared plus z minus z0 over r squared is equal to 1. Okay, I think they take it one more step there. Okay. And let's see if they do indeed do that. Oops, I could have left that on there. If x, y, z is an arbitrary point on the sphere, then the equation would be this. You do the square root equal r, and then square both sides, and you get this, and shown in this figure. Okay? Moreover, they left it in that form. They didn't do the other one. when y'all get into Cal 3, you'll probably change that slightly. If you do quadrant surfaces there, which usually that's where we put them, you have the last one that said where you have it equal to R. Okay. Moreover, the midpoint of a line segment joining 2 points, now this is completely different from that. Don't get it confused with this. This is another thing. The midpoint between 2 points, x1, y1, z1, and x2, y2, z2, is just the average of x1 and x2, comma the average of y2 and y2, comma the average of z1 and z2. So it's add them together, divide by 2. Add the x's, divide by 2, comma, add the y's, divide by 2, comma, add the z's, divide by 2. It's your midpoint formula. Okay? Pretty straightforward. I would have put this on a different slide. Otherwise, you're trying to figure out, well, where is that here? You know, it's not there. Okay. Now, they're skipping example 2. So let's go back and see if we can find some clean space to do example 2. This looks like some here. So let's hit it. All right. Find the standard equation of the sphere that has the points 5, -2, 3, and 0, 4, -3 as endpoints of the diameter. Okay? These are endpoints of a diameter. Now, what does that tell you? Anything? Can you get an equation, a standard equation of a sphere that has those 2 points as being endpoints of the diameter? What you think? Yay or nay? Did they just make up this problem, an impossible problem for you to do? Okay, and what would that give you? If you're at 2 ends of a diameter, you do the midpoint formula, where are you? Say again? You're in the middle of the diameter, and what do we usually call that point? The what? Pretty close, but the origin is usually 0, 0, 0. That's right. Huh? Okay. No, not quite. Oh, come on, folks. Okay. I'm a little sphere. There's a diameter. There's a diameter. There's a diameter. What's the midpoint of that diameter? The what? For what intersect? For all those diameters intersect? Yes. What is that? I hope you kick yourself when I say this. Say again? The what? The center! It's the center of the sphere. The middle of any diameter is right in the center of the sphere, right? Because the diameter exactly cuts it in 2. The midpoint there has to be a center. Okay? So, midpoint formula is a great thing to use to get the center of the sphere. Okay? So what is the midpoint? Can you tell me right now? Or do you need to do a little bit of calculating? Second?
5 plus 0 over 2.
Okay, which would be? 5 over 2. Positive 1. 0. That is the center of the sphere, which we were calling x0, y0, z0. Right? Now, what else do we need to write a standard equation for the sphere? We've got the center, which is the midpoint. you got to have a radius. Now, how do we determine a radius? Anybody? What is a radius? It's what? Okay, I know that. Okay. So, can we get that with just the information we've got here? How? Got a what?
First you do put the square root.
Okay, the distance formula. What will that tell you? What is?
That'll be the equation, standard equation of the sphere.
Okay. The distance formula itself will not give you the standard equation of the sphere. Okay? But what does a distance between these two, what is that called? The distance between two endpoints of a diameter. What would that give you? What do we call that? The distance between the two endpoints of a diameter. We call it the diameter of the sphere, don't we? Don't we? Isn't the diameter of the sphere the distance between the two endpoints of a diameter?
Oh,
Yeah. Okay. And what are we looking for? You said the other thing? A radius. A radii and diameter any way connected. How? Oh, I see. You just answered that part. The other people have to figure out the rest of it. How are radius and diameters related?
Radius is
Half of the diameter, of course it is. So if we get the distance between these 2 points, that's the diameter of the sphere, and then take half of that and you got the radius. So therefore the distance formula is what we use, that square root thing, and you tell me what it is. And this D stands for either distance or diameter is equal to I'm ready? Okay, the square root of okay, can I just wait. You're doing midpoint again, aren't you? We want the distance between these two endpoints. That's your diameter, right? It was a long time ago we did one of those, like 12 minutes. What do we put in the distance formula between those 2 points?
4 minus 2.
Okay.
4 minus 2.
Let's start there.
5.
Ah, why not? And what's that? Okay, -5 squared plus 4 minus 2 or 4 minus a minus 2.
Yeah.
Oh, that's what I meant. Yeah, okay.
6.
6 squared plus
3.
which is really -6 squared. All right. Feel like a dentist here. That's the square root of -5 squared. 25 plus, say again, 36 plus 36 equal the square root of 72 and 25, huh? Say that again.
5 plus 6 plus 6.
Yeah, okay. That would be 17. Carry a 1. Okay, I'm waiting. Say again. 17. 25 plus 36 plus 36? Oh, no. Don't make up any new rules on this here. The square root of a sum is not the sum of the square roots. No, that's not a linear relationship. It's a square root relationship. Rule of order of operation, you do what's inside first, then you do the outside. So what does that give you? Yeah, you add it first. 97? Right? Okay. And whatever the square root of 97 is. That's a weird number. We're just going to leave the square root of 97. Okay? That is the diameter of this circle. What are we really looking for? The radius. And what's the radius of that circle? Someone told me before. A long time ago. About 4 minutes. How is radius related to diameter? Half of it. So the radius will be that over 2, right? Agreed? Okay. Are we ready now to write down the standard formula for the equation of that sphere? How does it go? Okay, here it has x's and y's. It's x minus 5/2 squared plus y minus 1 squared plus z squared is equal to that's r. Square it 97 over 4. So it'd be 97 over 4. That's it. There's your standard equation. X minus 5/2 squared plus y minus 1 squared plus z squared is equal to 97/4. Good deal. Make sense? All right. So that was example 2. So let's get back to vectors in space. Okay, how are we doing? We got some time. All right, in space, vectors are denoted by, okay, how do we denote a point on the plane? Any point on the plane. This, how do we denote that?
X and Y coordinates.
Yes, an ordered pair, x coordinate, y coordinate, right? So how do you think we do it in space? Yes, we have an ordered triplets. Now notice that ordered, meaning the order does matter. It's always the x first, the y second, and the z third. And there's always 3 of them. Okay, so ordered triplets. And for a vector, that would be v1, v2, v3. This is in vector notation, for component notation. The 0 vector, of course, we've got to have in 3 spaces as well. And that would be 0, 0, 0. Right? Now, remember, what's weird about 0 vector? It has no direction and it has no length. Okay, every other vector has a magnitude and a direction. 0 vector has neither one. Okay, so that's the top point. You have to have it just to complete the sphere, not the sphere, complete the set, you might say. Now, your unit vectors, standard unit vectors here, just extend one more digit. 1, 0, 0 is your I vector, the J vector, unit vector, 0, 1, 0, and the K, of course, is 0, 0, 1. Standard unit vector notation. Then to get from here to here, the V's are the same, Here we just do V1I plus V2J plus V3K. Pluses in between rather than just commas. Okay? And this is what, when I was growing up, we called component notation. So these are your components in each of the three directions. Nowadays, when they've added the angle bracket representation, that's what I call component notation. Okay. So, you do sum V1 times X, that might get you out to here, then some V2 times your J vector, however many times that goes, and V3 times the K vector, and that's how much you go up there. So, that's how we represent the vectors in three space. This notation or that notation. Either one. Whatever fits your problem best. Okay? If V is represented by the directed line segment from P, which is P1, P2, and P3. Now these are coordinates of a point, not components of a vector. And Q, second point, your terminal point, that's Q1, Q2, and Q3. These are now your, if V is represented by those two, we always do this is initial, that's terminal. PQ, arrow pointing in that direction. Okay, as shown in this figure, then the component form of V is written just like we did before. Now here, the order matters. Remember on the distance form, it really didn't matter which one you wrote first, because you square it. This one, it does matter, okay? V is written by subtracting the coordinates of the initial point from the coordinates of the terminal point. In other words, terminal minus initial. So the V here would be Q1 minus P1, comma, Q2 minus P2, comma, Q3 minus P3, and put those in angle brackets. Those are your components. Make sense? Just one more extension from what we had on the two coordinate or vectors in the plane. So here we have, here's P1, here's point P. These are coordinates of the point, P1, P2, and P3. Q up here, Q1, Q2, and Q3. Now, I can't, for the life of me, look at that and tell you which quadrant they're at. Since they put a construction line here, I know that's positive X, positive Y, and positive Z, so this has to be in the first octave, okay? But without this, that could have been on the plane, it could have been back there somewhere, this could have been back there somewhere. Until they put these construction lines here, you can't really tell where it is, okay? So this is the vector V. Q1 minus P1 is the first component, X component, Q2 minus P2 is the Y component, Q3 minus P3 is the Z component. Okay. Now, a few of the characteristics of vectors in space. If U is U1, U2, V2, U1, U2, U3, V1 is V1, vector V is V1, V2, V3. There's vectors in space. C is any old scalar, any real number in the world. Okay? Then for these two vectors to be equal, that's true if and only if U1 is exactly the same value as V1, U2 exactly the same value as V2, and U2 exactly the same value as V3. Okay? Only if that's true. And if that is true, they're equal. Now, they may not look the same. If U1 was 2 and V1 was 6 over 3, yeah, it's the same value. Or square root of 4, yes, it's the same value, okay? Even though they may not look the same. Now, in component form, if V is represented by a directed line segment from P to Q, initial to final, then V is, just like we did on the last slide, V1, V2, V3 is Q1 minus P1, comma, Q2 minus P2, comma, Q3 minus P3, comma, angle bracket notation. There you go. The length of the vector, just like we did before, is, except a little bit of a clarification here, you can either do the square root of Q1 minus P1 squared plus 2Q minus P2 squared plus Q3 minus P3 squared. You can do it that way, but yeah, you already know what those things are. So that's just V1 squared plus V2 squared plus V3 squared. same way we did it on 2 space, only had 2 components. Unit vector in the direction of V. Exactly the same definition as before. That vector V divided by the magnitude of V. What's the magnitude of V? That's the length of V. This thing right here. So that would be V, which is V1, V2, V3, divided by that magnitude, whatever that is. Now, of course, V cannot be the 0 vector because it has no magnitude. Okay. Can't divide by 0. Vector addition. Add 2 vectors together, you add their components together. That's why component notation is the way to go. Don't even start trying to do this geometrically. It's hard enough just to figure out what a vector is on a plane to try to add on a plane. No, don't even mess with it. Just do component notation. V1 plus U1 plus U1 plus V1, vector addition, comma U2 plus V2, comma U3 plus V3. That's it. Okay? Scalar multiplication. If you're multiplying the C scalar by either one of those vectors, they're doing V, then that's just C times V1 plus comma CV2 plus comma CV3. Okay. That's how you do that. It's exact extension from 2 space. Nothing really new there. Let's do example 3. Okay, I think we've got time. All right. Find the component form and the magnitude of the vector V having initial point -2, 3, 1, terminal point 0, -4, 4. So let's first do V in component form. And what would that be? You tell me. Anybody? We're looking for component form. What would that be? Hasn't been that long since we did it. Has it? I want to go back a slide or two. Component form is Q1 minus P1, comma 2Q2. You see it? So what would this be? Anybody? Please? It's not that hard. 0 minus a -2, comma, -4 minus 3, comma, 4 minus 1. Close. And that would be 2, -7, 3. Done. Pretty easy. Next thing it asks for is the magnitude of V. How do we get the magnitude of V? There's a symbol for it. It's also called the length of the vector, if you wanted to use that term. What would that be? The square root of 2 squared plus -7 squared plus 3 squared, which would be, in this case, the square root of 4 plus 49 plus 9, which would be, that's, second, 62, isn't it? 62, square root of 62. And maybe you can pull something out. I'm happy to leave the square root of 62. Okay, so there we found the magnitude of the vector. Okay? Then find a unit vector in the same direction of V. So we're looking for a unit vector this time that's in the same direction of V. Anyone tell me what that might be? Say that again. 1 over root 62. That's the road that goes, no, I'm sorry. Times. Okay, right. Okay. You could either do that times the vector 2, negative 7, 3, or you could, like you were saying, put it as a vector 2 over root 62, comma, negative 7 over root 62, if I could write, comma, 3 over root 62. There is the vector. There's the unit vector in that direction. Now, how do you know that's a unit vector? You can determine its magnitude by squaring this, plus squaring that, plus squaring that. This will give you, when you square it, 4 over 62 plus 49 over 62 plus 9 over 62, and 9 plus 49 is 58, plus 4 is 62. 62 over 62 is 1. Yep, that's a unit vector. All right, I think we've done all the pieces that they wanted us to do with that. Okay, so let's see how they did it and if they got it right. Any questions before I erase it? Okay, so that will be the component form of V, which is the easiest one to deal with, just like y'all did. The vector, which first component is Q1 minus P1, second component Q2 minus P2, third component Q3 minus P3. That would be 0 minus a minus 2, comma, minus 4 minus 3, comma, 4 minus 1, whoops, which is 2, negative 7, 3. Exactly what we got. Then to find the magnitude of that, we just square each component, add them together, take a square root. Gives you root 62. Got it? Same thing we did. And then to find the unit vector, put those together. The vector V divided by its magnitude, which would be, and they wrote it this way, which is perfectly fine. It's a little more concise. 1 over root 62 times the vector 2, negative 7, 3, but I think they then turn around and write it like this too. The vector 2 over root 62 minus 7 over root 62, 3 over root 62. That gives it to you. Any questions? All right. That was example 3. Now, top of page 765. Whoa, stiff. Okay. Recall from the definition of scalar multiplication that a positive scalar positive scalar multiples of a non-zero vector V have the same direction as V, if it's a positive scalar, okay? Whereas a negative multiple will have a direction in the opposite of what the original V was. In general, two non-zero vectors, U and V, are parallel when there is some scalar C such that U is equal to C times V. In other words, they are the same direction, though maybe opposite directions, okay? And maybe different lengths, that's fine too, but those are going to be parallel. They've got to be, okay? So the definition of parallel vectors, two non-zero vectors, U and V, are parallel when there's some scalar C such that U is equal to C times V. Any scalar that would work, okay? For example, in this figure here, the vectors U, V, and W are parallel because U looks like it's exactly twice V, and W is equal to exactly negative 1 times V, or negative V. So there is a scalar, 2 or negative 1, or pi thirds, or negative E over 4, you know, whatever it is, if it's just some scalar that multiplies by 1, to give you the other, okay? Can't be a variable, has to be a scalar, constant. Okay, so here is example 4. Vector W has initial point 2, negative 1, 3, terminal point negative 4, 7, 5. Which of the following vectors is parallel to W? Okay? how are we going to work that problem? You tell me. Second? A little louder. Okay. Okay. Okay, right. Okay, got it. Okay, we need to find what the vector W is. So the vector W, we're going to do first, is equal to, which is? Negative 6. Is that what you said? Okay.
6.
No, I don't think so.
Oh, it's 7. Oh, 8, sorry.
All right. Okay, it's multiple choice. Okay. Next. 2. Okay. Now, which of those two vectors, or both, would be parallel to W? Would U be? Second? U? Yes, it is. Because to get from U to V multiplied by negative 2. Negative 2 times 3 is negative 6. Negative 2 times negative 4 is positive 8. Negative 2 times negative 1 is positive 2. Yes, that one works. How about V? Second? V is 2. Is that what you said? Okay, what's the multiple? Negative 2. Yeah, negative 2 times negative 6 is 12. Negative 2 times 8 is negative 16. But negative 2 times 2 is? Negative 4. Doesn't work. Close, but no cigars. So that one is not parallel to W. See how that works? Let's see how they did it. Let's erase this. And they started off by figuring out what W was, negative 682. Look at that, they got it right. And then because U is exactly negative 1/2 of W, or in other words, W was exactly negative 2 times U, then you can conclude U is parallel to W. The B one, though, we needed a scalar that would do that. Let's see if we can work. The ratio of those, 12 is equal to negative 6 times C. That would have C equal negative 2. Okay. Negative 16 is equal to 8 times C. That would be C is equal to negative 2. Fine. But 4 is equal to 2C. C is equal to positive 2, not negative. So therefore, it's not parallel. Good deal. This means that the equation that has no solution, the vectors are not parallel. Whoa, is that all, folks? Okay, that was example 4. They skipped example 5. Do we have time for example 5? No, not if I'm going to do the announcements, I don't think. Will it? Okay, let's stop. We'll pick up with example 5 next time. Okay, and homework exercises here, do either 5 or 7. They're both at calcchat.com. Neither are at CalcView. Do either 9 or 11. They're both at CalcChat. 9's at CalcView. Do any of the odds 13 to 23. They're all at CalcChat. None of them are at CalcView. Do 25 or 27 or both. They're both at CalcChat. 25's at CalcView. Do any of, whoa. That's pretty interesting. Yeah. Do any of the odds. Now, they're doing some things here we haven't done, but you should know. So, try them. 29 or 31 or both. They're both at CalcChat, neither at CalcView. Do either 33 or 35. They're both at CalcChat. 33's at CalcView. Any of the odds 37 to 41. They're all at CalcChat. 39's at CalcView. Either 43 or 45. They're both at CalcChat, neither at CalcView. Any of the do 47. It's a CalcChat but not CalcView. Do 49. It's a CalcChat, not CalcView. 51 or 53, they're both a Calc Chat. 51's a Calc View. 55, it's a Calc Chat, neither a Calc View. 57 is a Calc Chat, not a Calc View. Either 59 or 61, they're both a Calc Chat, neither a Calc View. And 63 or 65, they're both a Calc Chat, 63 is a Calc View. Okay, we'll stop there and pick up the rest of those later. Now, let's talk about where we go from here. Okay, number one, we have class Monday. Okay, that's our last day of class. Now, William, when he was here last time, asked if I could get the final ready early so you have a weekend to work on it. Well, I knew I didn't have time to do it before today, but maybe this afternoon I can. So what I'm going to do is get it ready. I do my typing in WordPerfect because this equation editor is so much superior to Word. It's just so much easier to use. It does it well, right, and everything. So I'm going to do it in WordPerfect. But then I'll take it down to the records office and get them to scan it, put it in a file, give me the file, I'll send it to you. It's a PDF file. It'll go to you, and I'll put it on Blackboard, so it'll be there. Now, if you come Monday, I'll have paper copies as well, so you don't have to do it if you don't want to. But if you do, and William said he did, and a lot of people aren't here, I don't know. So anyway, that will be, I'll try to get that done this afternoon. Okay? Okay. We have class on Wednesday, and that's why I'm going to have to try to guess how far we're going to get on Wednesday. We have just a little bit more to go in 11.2. Then we've got 11.3. I think we can get that done. 11.4. I'm going to we'll try our best to get that done. I doubt if we'll get past 11.4. But we'll see. Okay. If we do get there, you may not have any questions on the test for that. We'll see. Okay, so that will be Monday. Now, when are the tests due? Okay, other thing, time out. Let me say this before I forget it. I forgot it in my last class, so let me say it now. I found out, maybe I didn't forget. I found out yesterday that they finally opened the student course evaluations.
Oh, yeah.
Yeah, you have seen that. I've been asking earlier, but I never saw it, so I quit asking because I thought it was too late in the term. They opened it last week, wasn't it? That's what they told me last night.
I think I got it Monday.
Monday,
Yeah.
okay. So either this week or last week is when they opened it. Please, folks, do your student course evaluations. Now, that we always do them fall and spring, and that's great. We get Lawson input. I really want to hear what you folks who are transient students are thinking too. I want to hear what your Lawson students are thinking, but I want to know how I would like to see it from all of them. Now, I'll never tell who did what. I can't do that and don't want to do that. But I want to see the composite, okay? That's all I get to see is the composite. So I want as many of you as can to do your student course evaluation. It'll be open through finals week and probably a little bit beyond, but please do them. Don't take off and go home. You'll never think of doing it again. So sometime really soon, do your student course evaluations. Okay. Now, so next week we have class on Monday, and I'll hand you your paper copies of the final if you didn't pull it off the blackboard. Okay? Now, when are those finals due? Tuesday, Wednesday, or Thursday. Okay? Not much time, so I'm going to try to make them fairly straightforward, but this is not all that easy of stuff. I thought it was pretty easy until I started asking questions today and found out how hard it was, okay, for some of you. So hopefully you'll pick up on it and go. But anyway, you got to get it to you Monday, Tuesday, or Wednesday. Tuesday, Wednesday, or Thursday. Let me give you my schedule on those days. On Tuesday, I'm here on Bessemer campus, okay? I don't have anything because there's no classes on Tuesday. It's finals from 7:45 until 12 noon. At 12 noon, I'm giving a final in this room, and that will be approximately 12 to 2. I doubt if it'll take them that long, but I'm going to give them that long to do it, at least. 12 to 2. Then I'll be back in my office from 2 to 3:30. 3:30, I have to leave to go to the Birmingham East Campus That's where the folks have been taking my physics class, and they're going to be turning in their final either Tuesday or Thursday, either day. So I'll be there from 4 till 6, both days. Now, let me tell you where my office is. Not all of you at once. Students may not know. We're right here in this classroom, right here. Go out the door here, angle left, there's a little half-flight of stairs right there. Go all the way to the end of the hall. Before you bump into the wall, the last door on the left is the stairwell. Go right before that on the left is my office. The mechanical room and the stairwell. Right across from 256. My office number is 265. So if I'm in class, like giving a final, or I'm over on the Birmingham campus or something like that, and you want to leave your materials, slide them under my door. That would be perfectly fine. And by the way, the research papers are due by Monday. Okay? Even more so, your test. I want to return all tests to you Monday, near the beginning of class. Which means if I don't have your test in, it's a 0, okay? So please get your test in to me by first thing Monday morning, okay? And then that's the first 2 tests. I'll be giving you your 3rd test then, so you have time to work on that. Your research papers are due anytime Monday. If I get them Tuesday or later, you're losing points. Okay, I'll still grade them, but you're going to be losing points. So get those into me Monday as well. Okay, so that's Tuesday. I told you where I am. Okay, Wednesday, I'm on this campus all day long. 7:45 in the morning till 6 o'clock in the evening. No finals, nothing, in my office, 265 the whole time. Oh, and on the Birmingham campus, let me tell you that. Birmingham East Campus is the Ethel Hall Health Professions Building, and it's room 103. So when you go in the building, there's a V like this, take the left, and it's the first classroom on the left. It's just past the restrooms. It's right, really easy to get to. The office is right in front of you. You can ask them. They'll point right there. Okay. So that's where I'll be Tuesday and Thursday between 4 and 6. So if you want to bring them there, you can. If you want to slide them on the door here, you can. Okay. So that's Wednesday here all day. Thursday here from 7:45 in the morning until 3:30 in the afternoon. 3:30 I head to Birmingham East Campus. I'm there from 4 to 6. Now, if it's not convenient for you to take it there, 4 to 6 on Thursday, you can slide it under my door, and even though I'm not coming back here, I'll get it first thing Monday morning and grade it and get it done. Now, I don't want everybody turning everything in that way, but if you can't catch me and want to just leave it there rather than try to chase me down on a different campus, you can do that. A few of them I can get graded. Grades are due, for us, are due noon on Monday. They're really inflexible about that, so please get it in. If I don't have all the material by noon, in time to grade it by noon on Monday and get it in there, you're going to get an incomplete, an I. And then if I get the material, or if it's there, I just didn't have time to grade it, I'll grade it and change the I to 5. I've got to turn in a grade by noon on Monday. So too many papers under my door Thursday afternoon. I'm not going to get them all graded. I'll get as many as I can. Everybody else will get I's, and then as soon as I get them graded Monday afternoon, I'll change the I's to grades. And here's one more thing. If y'all have been checking grades or anything else through Student Suite, on Monday, that will not be open to you because, believe it or not, we have something like 16 ports. And therefore, if more than 16 students are looking for their grades, which could easily be the case, the faculty can't get on there to put the grades in. So they close student off of the Student Suite on the days we're entering grades, so we can get on there to enter the grades. But guess what, folks? Go to Blackboard first. Everybody can always get to Blackboard. That's where I do the averaging. That's where I figure the grades before I put them on the suite. So go to Blackboard on Monday if you're looking for your score and see what it is. Okay? Any questions? Good deal. We'll see you Monday. Have a good weekend. Get all your tests into me. Have you got tests here? Yeah, but you did get it.
I can't go to the Blackboard, but I just wanted to finish sharing my first test score.
First test score. Okay. Hold on just a second.
I have my test due as a second.
Okay.
And I do have my paper done. It's not
Fantastic. Okay. Let's see.
So I can email it.
Bailey. You need to see it?
Yeah, that's all I need to see.
Oh, just-
I can email that paper to you.
Okay. Here's the only thing about email.
Okay.
I grade what I print out.
Okay.
And I've had already this term, someone sent me a paper, and I know they must have center, what do you call it? Oriented, whatever, there's a better name for it. Their title, and they forgot to take that off, and they typed the whole paper with center justified. I have to grade it, and they're losing points. Okay,
Well,
so be sure
As long as
it's
I get,
exactly
as
what
long as I
you
get
need.
both tests to you, both things to you Monday morning, we're good.
Yeah, that'll be fine. Yeah.
All right, you're gonna be in here.
I'll-
Say I get here like 30 minutes before this class starts at 10:30.
Yeah, okay, yeah. My first class is 8 to 10:40, and then I usually run down and pick up a little snack or something in my office and come back up here. So yeah, if you turn it in when you first get here. If you're here at 11, give it to me, then you're fine.
Can I see my first test for you?
Sure.
Okay, and it's okay if we turn in test 2 with the paper in class Monday?
Yeah, that'll be fine. Beginning of class. Okay? 87.
Okay, all right, thank you.
Yeah, good score. Okay, I just recorded that, by the way.